This video is going to focus on two main concepts. The first is something called the addition rule, and the second concept will be something called the rule of complements. And they're sort of separate but similarly important rules that we're going to need to handle probabilities. So starting with the addition rule, what if we're interested in the probability of multiple events occurring? So if we're interested in multiple events, then we're going to need a way to deal with that. And we're going to call these multiple events. There's more than one event that we're interested in. We're going to call that a compound event. So this is going to be our first definition here. A compound event is an event that's made up of two or more other events. So it is an event formed by combining two or more other events. So we'll use two different letters when we deal with an event like this if we're combining two different ones. So we'll have A and B. If we have events A and B, and we want to combine them in some way, we might want to know the probability that basically one or the other or both occurs. And we'd call this a compounded event A or B, basically. Before we jump into this too much, I want to focus on this word or here. It's actually a more important word than we might think, because I want to define the concept of what it means when we say A or B. So I'm interested in finding the probability of A or B. This is going to be the concept that we're going to be interested in looking at. I want to figure out exactly what I mean when we say this word or. In the plain English language, the word or has really two distinct meanings, and we interpret the meaning based on the context of what somebody's talking about all the time without even thinking about it. So, for example, if you go to a restaurant and you get a hamburger or something, they may ask you if you want ketchup or mustard. And when they ask you if you want ketchup or mustard, what they really mean is, do you want ketchup by itself, or mustard by itself, or both? Or both is also an option. You can always get ketchup and mustard. Whereas if you go to a grocery store and they're bagging your groceries and they ask you if you want, paper or plastic, typically they really mean one or the other. You usually don't get both. The same thing happens like with my kids when it's time for dessert. If I ask my daughter, if I've got two cookies or something like that, and I say, do you want, this cookie or that cookie? What I really mean is you get one and your brother gets the other one. You just get to pick first. I don't mean this cookie or the other cookie or both. It's an exclusive or. You're only allowed one. And so this is the distinction. There's inclusive ors, where we mean really you can have A or B or both. That's inclusive. And exclusive ors, where you're only allowed to have A or B, but definitely not both. And in this case, the or that we're going to be talking about is the inclusive or. So for us, when we say A or B, what we really mean is we're interested in the probability of A or B or both. And this or both is what makes it an inclusive or. So keep that in mind. That's what we're going to be interested in, is when I say A or B, I mean the inclusive version of the word or. Okay, so I think the easiest way to deal with these compound events, probability like A or B type thing, is to actually use examples. And so let's use some examples that we're already kind of familiar with because we've seen them in the previous videos. Let's roll a six-sided die. And I want to ask the probability of a compound event made up of two different events. So the first event, A, I want to let A be the event of rolling an even. And event B, I want to let that be the event of rolling a multiple of 3. And again, when I say a multiple of 3, we talked about this in the last video, it means we're counting by 3s. So 3, 6, 9, 12, 15, and so on. We already know that our sample space, because we've done this in the previous video, our sample space is going to be made up of all 6 possible outcomes. So 1, 2, 3, 4, 5, and 6. So again, the size is 6. We have 6 possible outcomes. How many of those outcomes satisfy each of these events up here? So if we're rolling an even, that's rolling either a 2, a 4, or a 6. And we can see that this has a size of k equals 3. I'm going to call it k1, or maybe k with a little subscript of a to know that this is the size of the event that we're associating with a. And our second one down here is rolling a 3 or a 6. And so we'll say the size of that, how many outcomes satisfy that? There's 2 outcomes that satisfy that. And so when we say, I want to know what's the probability of A or B, or both, I think that's too many R's. Occurring, just one R maybe? Yeah, it looks slightly better. No idea. Okay, so what is the probability of A or B occurring? So what we're looking for is, again, P of A or B. And we don't know what that is. So I want to start off, before we jump into the probability of A or B occurring, let's look at the two probabilities individually. I want to find the probability of A and the probability of B separately and see if we can relate that, the answer to these two questions, to the answer to this one. So individually, if we look at the probability of event A, which is rolling an even, it's 3 out of the 6 possible answers. So the answer on this one is 3 out of 6, which simplifies to a half. And similarly, for event B, that's rolling a multiple of 3, there were only 2 outcomes that satisfy rolling a multiple of 3 out of the 6 total. So this has a probability of 2 out of 6, which would simplify to a third if we wanted. So maybe the answer is to simply add these two pieces up. If I'm interested in the probability of this occurring or the probability of this occurring, maybe I just add these two probabilities up and we get our answer. So let's take a look at what would happen in that case. If I just said that this is equal to the probability of A plus the probability of B, we would get, adding these two values up, we would get from this part, we would get 5/6. Where did I get that number? Well, I got it from adding the 3/6 to the 2/6. When we add fractions, remember we need a common denominator. So I'm not going to add the 1/2 and the 1/3 because they have different denominators. We can't combine them in the same way. We have to find a common denominator. If we just go back to before we simplified, they had the same denominator. It was out of 6. So 3 out of 6 plus 2 out of 6. We add the numerators, 3 plus 2, that gives me the 5, and we keep the 6 for the bottom. So this gives me 5/6. Is that the correct answer? Do I have a 5 out of 6 chance of rolling either an even or a multiple of 3? And the answer is no. I can't just add those together. Because if we look at the event A or B, So now that I'm going to come up here, we have A and B individually. Let me just write what A or B is. What is everything that satisfies either A or B? Let's do it this way. So what is the list of outcomes that would satisfy either rolling an even or a multiple of 3? Is 1 an even or a multiple of 3? No, so we wouldn't include the 1. Is 2 an even number or a multiple of 3? Yes, it's an even number, so we'd include the 2. What about 3? Is 3 an even number or a multiple of 3? Well, it's not even, but it is a multiple of 3, so we would include that. So as long as it satisfies at least one of them, we're including it. What about 4? Is it an even or a multiple of 3? Yes to an even, no to multiple 3, so we would include it because it's even. What about 5? Is 5 an even or a multiple of 3? No, we can see, and clearly it's not in either list, so we're not going to include 5. And then lastly, 6. Is 6 even or a multiple of 3? In this case, it satisfies both. It's both even, and it is also a multiple of 3, so we would need to include that number as well. And so if we look at the actual result of how many things we got here, so what is the K of A or B? It's equal to 4. It's 4 out of the 6 things. So this probability needs to be equal to 4 out of the 6. But when we just added these two other ones together individually, we got 5 out of 6. So we're off. We should get that this probability should be 4 out of 6. But we just got 5 out of 6. So what's the issue? The issue is this 6, that last term that we considered, shows up in both lists. So I'm counting it here when I include the 3 out of 6 that make up the probability of A. And I'm also including it again here for event B in the 2 out of 6 that make up event B. I'm double counting it. I'm counting it twice. So we need to take off anything that got double counted. And the way that we're going to write that is we're going to remove the probability of anything that's in both A and B. So we're going to use the word and, A and B, to represent things that show up in both lists. So for example, if we were, in this case, A and B, if I come back over to this side over here, if we did A and B, that event is made up of just the 6 by itself. It's the one thing that shows up in both lists. So what is its K value of A and B? There is one thing that shows up in that list. And so we would subtract off 1 out of the 6 possible values. And that would give us the correct number that we're looking for, which is 4/6. So this formula that I've got written right here turns out to be what we call the general addition rule. So this gives the general addition rule. The general addition rule says that the probability of event A or B is equal to the probability of event A plus the probability of event B minus the probability of anything that shows up in both A and B. This removes anything that gets double counted. The book also talks about a second rule, if you read the book, something called the mutually exclusive addition rule. And we'll talk about what it means for something to be mutually exclusive in just a minute. But I want to tell you that this rule will work in 100% of cases, so we don't even need that second rule. So just keep that in mind. Stick to using this one. We don't need to memorize 2 separate rules. This one will always work. So there's different ways to kind of visualize this. We just did it with the actual numbers to justify this equation. But another way to think about it is using something called Venn diagrams. So I think it's worth at least looking at. So we can justify this. Sorry. Using Venn diagrams. In a Venn diagram, you may have seen before, it's the type of thing where you've got like overlapping circles, and we use those overlapping circles to represent different things. So we start off with like a box. This box is what generally corresponds to what we think of as the sample space, and then we have events within it, and those events may have overlap or they may not have overlap. And so I'm going to label the one on the left here A, the one on the right B. If we go back and treat the A and the B the same way that we did up here, let's get it all on the page at once. So if A is rolling an even and it involves these particular outcomes, 2, 4, and 6, and B is rolling a multiple of 3, so it has 3 and 6, here's how we would write them all out. A would have 2, 4, and 6, and B has 3 and 6, but the 6 needs to go in the part in the middle that's in the overlap. It's in both A and also in B. And that's 4 of the 6 outcomes. So we have 2, 3, 4, and 6. We're missing the 1 and the 5. Where do the 1 and the 5 go? They go out here. So we'd have a 1 and a 5 out in the rest of the box. And we've now taken care of the entire sample space. We have 1, 2, 3, 4, 5, and 6. These fall outside of those two events, but still in the sample space, right? They don't satisfy event A, so they're not in that circle. They don't satisfy event B, so they're not in that circle, but they are in the overall box of our sample space as indicated right here. There's the 1 and the 5. So this is what the picture would look like if we did it with a Venn diagram. And if you think about what the shapes represent, if I talk about the region A or B, the region A or B, and I talk about its probability, you can think of it as being sort of analogous to the area. And if this is sort of our A, and this is our B, and within them they have, right, this region of overlap, that's what it kind of looks like. That whole region represents the A or B. And our argument is that when we take the probability of A or B, it's equal to the probability of A, which is just going to be a circle, right? A represents this whole circle on the left. And I'm going to add to that the probability of B, which is the whole circle on the right. So we're adding another circle. And we want these areas to match up, and right now they don't. Right? If you think about it, over here, I don't have two full circles. I can kind of break these ones up so they look the same if I chop this one, a section out like this, and similarly over here. What we've really done is cut up this circle into a sort of a big crescent moon shape, plus like a little football shape. So we've got, over here, we've got 2 crescent moons and 1 football, but over here I've got 2 crescent moons and 2 footballs. And we need to remove one of the footballs in order to get all of the areas to actually match up. And that football represents the A and B, as we mentioned a minute ago. It represents anything that shows up in both A and B. So that's the region of overlap. So this is another way to kind of justify the way that we have the formula set up, looking at it from the perspective of a Venn diagram, which is really helpful for some people that are very visual. This shape, sort of butt print shape, if you will, is made up of 2 crescent moons and a football. And we can get that by having 2 circles that we cut up into our 2 crescent moons with 2 footballs and then subtracting off one of the footballs. So that is the idea. Okay, so this is again our general addition rule. We're going to be using it. We can use it in lots of situations where, for example, if I tell you what some of the values are, if I give you that, I tell you the probability of event A is 0.25 and the probability of event B is 0.36 and the probability of A and B is equal to 0.1. What is the probability, oops, let's make that up here a little better, probability of A or B? So in this case, I've basically given you 2, or of the 4 different components that make up our equation for our general addition rule. We have, this is 1 piece, 2 pieces, 3 pieces, 4 pieces. I've given 3 of the 4. And as long as I give you 3 of the 4, you should be able to figure out what the remaining 1 piece is. So in this case, the piece that we don't have is the piece over here on the left. The probability of A or B is what we're trying to find. That's what's being asked for, but I'm giving you all of these other pieces. So it's telling us that it's the probability of A plus the probability of B minus the probability of A and B, right? That's just my general addition formula. And we just plug in the numbers. What was the probability of A? It was 0.25. And to that, I add the probability of B, which was 0.36. And from that, I subtract off anything that showed up that was in the overlap in both A and B, and that's 0.1. And if we add those numbers up, when I add these two numbers together, I'll get 0.61. So we can just do this on a calculator. Those two add up to 0.61. And then I'm subtracting off 0.1 from that, which you can think of as 0.10 if you want to add in that extra zero as sort of a placeholder. And when you do that subtraction, we should get 0.51. That is our result for the probability of A or B. So thinking about this from a strictly mathematical point, I don't even know what the event A represents. I don't know what the event B represents. Just looking at the numbers, we can figure out what that remaining value is. And again, in this case, it just so happened that we were given all three values that showed up on the right, and we were solving for the unknown piece over here that was on the left. But I could give you the piece on the left and two pieces over here and have this be the unknown, and we could still figure it out. We would just have to do a little bit of algebra. So keep that in mind. Maybe we can do another example of that at some point. But the idea is we could just rearrange the different values. And so, yeah, I guess what the heck, let's just do a real quick one right now. What if I told you the probability of A or B is equal to 0.45, that the probability of B is equal to, I don't know, 0.25, and the probability of A and B is, let's let that be 0.1 again. What is the piece we're missing? So I've given us the A or B, the A and B. This is the piece, probability of A, that we're missing. So what is the probability of that piece that's missing? So basically what we've got right now is if I plug them into the same formula, on the left, we'd have this piece. Right? So we have that 0.45 is equal to the probability of A, which is the piece we don't know, plus the probability of B, which we just saw is 0.25, minus the probability of A and B, which is 0.1. And so we have an equation here where we have three of the four pieces given as actual numbers, and the one piece that we don't know is right here, and we'll just have to solve for that. So I can simplify these two numbers first. I can take 0.25 and subtract off 0.1, which again, maybe it's easier to write it as 0.10 to have that 0 as a placeholder. But you can do this on a calculator if you'd like. So 0.45 equals the probability of A plus, combining these two pieces together, 0.25 minus 0.1 is going to give me 0.15. I need to isolate this piece all by itself. So right now it has this 0.15 added to it. I need to undo that addition to get this piece by itself. So that means I need to subtract off 0.15 from both sides. And when I do that, subtract 0.1 from both sides, I'll have this by itself. I'm going to subtract this number off from both sides. And on this side, when I subtract it off, it'll just cancel out. And on this side, when I subtract 0.15 from 0.45, I will get 0.30. And there's our answer in that case. And same thing down here. This would be our P of A or B. Might as well actually circle it. Or box it, I should say. Not much of a circle. Okay. So here's how you can use the general addition formula. You'll see some problems like this in the homework. I mentioned the concept of things being mutually exclusive a couple of minutes ago. Let me define what that actually means. So what does it mean if two things are mutually exclusive? Mutually exclusive events, so, and I should say that, mutually exclusive events. These events have no overlap. So there is nothing in common between the two. So going back up to our example, way back up here, rolling an even, rolling a multiple of 3, they are not mutually exclusive because they shared the 6. 6 showed up in both. So basically, if you look at the Venn diagrams, things that are mutually exclusive don't have this overlap. You can draw them as just two completely separate circles. So visually, there is no overlap in the Venn diagram. Another way of saying it is the probability of finding something that's in that overlap, so of anything that's in both A and B, is 0 because there's nothing there. So if there's nothing in that overlap, the probability of the overlap, which is the A and B part, must be 0. So that's the picture. And what that means is if we're applying this idea to mutually exclusive events up here on the general addition rule, we can just add these two values together because there is nothing in the overlap, nothing gets double counted, so we can just leave this part off. The probability of A and B will be 0. So what are some examples of things that are mutually exclusive, say in the context of this exact problem that we just did? So what are some examples of some events where there's no overlap between the two events? Well, one example would be if we let A be rolling an even and B can be rolling an odd. Right? Even would be the 2, 4, and 6. Rolling an odd would be 1, 3, and 5. And there's no overlap. There's no commonality between those two lists. But it doesn't have to be a complete list like that. It could just be rolling a 1 is mutually exclusive from rolling a 3. Right? Those are two different outcomes, and there's no overlap between them. If you rolled a 1, you didn't roll a 3. If you rolled a 3, you didn't roll a 1. So rolling a 1 is mutually exclusive from rolling a 3. And I just picked 1 and 3 randomly. You could have done it with any other two numbers you wanted. Rolling a 1 is mutually exclusive from rolling a 4, and that's just as valid. So basically, anything where there's not overlap between the two events, that's what makes them mutually exclusive. And it'll slightly simplify the process up here when you use the formula, because this term, the A and B term, will be 0 every time when you have two mutually exclusive events. So just keep that in mind. That's really all we need to know about the idea of mutual exclusivity. So let's move on to the second big component. We're pretty much done with the addition rule. Let's move on to the rule of complements. So I want to start off, let's fill this in here. So I should just say, in this case, complements does not mean the same thing it does in plain English. Normally when we talk about complimenting how nice somebody looks today, or how well dressed they are, or something like that, that's spelled differently. Compliments with an I in place of the E here. This type of complement is a mathematical term, and it's a confusing term. So I want to see if we can come up with sort of a definition of this. But again, it's going to be something that's much easier to talk about in terms of examples. The definition is weird. So let me write down our definition. Okay, so if A is an event, then the complement of A which will be denoted using the letter A with a little c up in the place that we would normally put like an exponent. So it's a little superscript up there. So the complement of A, which is denoted with this A with a little c up there, is also an event. And in fact, it is the event that A does not occur. So some people like to think of it as kind of an opposite, and that's kind of a good starting point, at least, to think of what the complement is. It's kind of like an opposite, but it doesn't quite tell the whole story. So let's think about this really carefully by going through some examples. So if A is an event, there will also be another event called A complement, and it is the event that A does not occur. And so what it means is there's no overlap between A and A complement. They are going to be mutually exclusive events. If A occurs, it automatically means A complement is not occurring. If A complement occurs, it means that A does not occur. So that is the idea here. So let's just do some examples, because I think really that's going to be the easiest way to understand this. Let's say that we've got a class. Maybe there's, whatever, 30 people, doesn't matter, that just took an exam. So just like you guys. And we haven't gotten the results back yet. So maybe in this case, the class just took an exam, and we're interested in the probability that, I don't know, let's say that at least 18 of the people got at least a B or something like that. So let's let A be the event that at least 18 people earned a B or better. So 18 people got at least a B. What is a complement? How would we phrase a complement? It would be the event that, and so this is a kind of a way to cheat it. It's just throw a word not in here at the beginning. So not at least 18 people earned a B or better. Now, granted, this makes this person sound like they don't really speak English. This is a really awkward sentence. Not at least 18 people earned a B or better. So we need to find a better way to phrase it. But the idea behind it is the same. So either event A occurred, in which at least 18 people earned a B or better, or event A complement occurred, where not at least 18 people earned a B or better. So what's a better way of phrasing that? We would say maybe, so in this case, we would say that fewer than 18 people. Oops. Fewer than 18 people earned at least a B, or earned a B or better. That is a much more natural phrasing of the same idea. And so this is something that I think kind of helps people. Imagine we have a number line, and I'm going to put some numbers on here, and we really only care about the ones close to this number, this 18 that shows up right here. So I'm going to put 18 right here. Maybe we'll have 19 and 20 going this way, dot, dot, dot. And this side we'll have 17 and 16 going this way, dot, dot, dot. And I want to figure out basically which outcomes in the class. So just forget about the idea of a complement right now, and just think about this hypothetical. If we had a class, and let's just say there's 30 people in it, and we're interested in, just for some reason this question, 18 happens to be the number that we're interested in. There's only two things that could have happened in regard to this number 18 and people getting a B or better. Either basically 18 or more people got a B, or fewer than 18 people got a B. Those are the only possibilities. So what if exactly 18 people got a B? So this number right here in the middle that we've drawn. What does that outcome satisfy? If exactly 18 people got a B, what is satisfied? A or A complement? So if exactly 18 people got a B or better, is A satisfied or is A complement satisfied? Which one of the two is satisfied in that particular case? So if exactly 18 people, so if exactly 18 people got a B or better, that satisfies at least 18 people earning a B or better. It does not satisfy fewer than 18 people earning a B, right? Fewer than 18 people means probably 17 or less. So if exactly 18 people earned a B or better, that doesn't satisfy a complement. So that means that including this 18, our division is going to occur right here. Everything on this side, if 18 people earned a B, if 19 people earned a B, if 20 people earned a B or better, all of these satisfy event A, which is that at least 18 people earned a B or better. Everything on this side must satisfy a complement. So if 17 people got a B or better, that does not satisfy A. That satisfies a complement, which says that fewer than 18 people earned a B or better, right? So if only 17 people did, then this is true, fewer than 18 people. If 16 people did, this is still true. If 15 people did, this is still true. All of these cases over here, 17 people getting a B or better, 16 people getting a B or better, 15 people getting a B or better, all the way down to 0 people getting a B or better, those all satisfy a complement. And so this is kind of how we want to do this. And I think this diagram can sometimes be helpful. But between the two of them, between A and A complement, they are going to cover 100% of the possible outcomes. So if you combine them, so let me answer this question first. If exactly 18 people got a B or better, is A satisfied or is A complement satisfied? So 18, we said that goes with A. A is satisfied. So coming back down to here, if we combine, combining A and A complement, covers 100% of possible outcomes. They combine to cover 100% of possible outcomes. So we could do it with, something, pizza toppings. In our class of 30 people, event A is that if we sample our class of 30 people and find out who likes pepperoni on their pizzas, event A could be that more than half the class likes pepperoni on their pizza, and a complement would be anything that doesn't satisfy that. So it would be less than half or exactly equal to half, because I said more than half likes pepperoni. What's the complement of that? Well, either exactly half or less than half liking pepperoni. That would be a complement. That would satisfy a complement. So it's a confusing concept. So let's do some more examples and see if this helps. So let's do another example here. What is the complement of the phrase that follows? So I'm going to say the phrase A is that more than 15 people wear glasses. Right? Maybe I have a big, maybe it's the place I work. I work somewhere and I'm doing a survey about how many people wear glasses. Event A is that more than 15 people wear glasses. What is a complement? Well, it's that not more than 15 people wear glasses. Apologize, my handwriting is getting sloppy here. Not more than 15 people wear glasses. But again, that's a very awkward phrasing. So let's rephrase that into something that's a little bit better. But these are the only two possibilities. If you polled your family, or you polled the class that you're in, or you polled the place that you work, and you asked, do more than 15 people wear glasses? There's only two possibilities. The answer to that question is either yes or it's no. If the answer is yes, then A is satisfied. More than 15 people wear glasses. If the answer to that question is no, then it's a complement that's satisfied, that not more than 15 people wear glasses. So same question, and we can, again, draw a number line like this if it's helpful, but let's see if we can do it without the number line first. This number itself, exactly 15. What if exactly 15 people wear glasses? Which of these two is going to be satisfied? Well, event A is more than 15 people wear glasses, but that means, because it's more than 15, it means it doesn't include the 15 itself. It must be starting at the number 16. So this means essentially 16 or more. So a complement needs to be the thing that includes 15. So not more than 15 people wear glasses. A better way to phrase that would be to say 15 or fewer people wear glasses. That's a much more reasonable way to phrase this. And confusingly enough, on the homework, this may not be an option. Another way to phrase this would be to say fewer than 16 people wear glasses. And technically, all of these three statements here are completely equivalent, right? 15 or fewer means 15, 14, 13, 12, 11, 10, and so on all the way down to 0. Fewer than 16 also means 15, 14, 13, 12, 11, 10, and so on all the way down to 0. Right? Fewer than 16 means we're not including the 16, so the next smallest number is 15. Over here I'm saying 15 or fewer, so I am including the 15. And both of these are lists that are anybody between 0 and 15 satisfy both of these two statements here. So just know that as you're doing the homework, for example, even though, in my opinion, this second phrasing is a much more natural way to phrase it than this third phrasing, if it's multiple choice, this third phrasing may be the only option that you have. Then what I would consider the more natural phrasing may not be an option in the homework. So just keep in mind, the phrasing is going to be a little bit tricky on some of these, so just keep an eye out for it. I mentioned a minute ago that when we combine the two outcomes, they combine to represent 100% of possible outcomes. And what I mean by that is one of these two things has to be satisfied. If we take a survey in our class, no matter what the outcome of that survey is, either A is going to be satisfied or A complement is going to be satisfied. So if we take the survey in the class and it turns out 10 people wear glasses, well, then that means that A complement is the one that's satisfied. 15 or fewer people wear glasses because there's only 10. But if it turns out in our class that 18 people wear glasses, well, then A is satisfied. Any number you pick, any outcome we get will either satisfy A or it'll satisfy A complement. And between the two of them, they cover 100% of every possible outcome that it could occur. That idea leads us to something called the rule of complements. So one or the other must be true. Either A is true, more than 15 people wear glasses, or A complement is true, 15 or fewer people wear glasses. One of them has to be true, but they can't both be true. So one or the other must be true. 100% of the time, one of them will be true, but never both. And what this means is that we get something called the rule of complements. And the rule of complements basically states mathematically what we just said in words. If I take the probability of event A plus the probability of event A complement, together those two things have to add up to 1. because they have to add up to 100% of all possible cases that could occur. They're mutually exclusive, right? There's no overlap between them, but one of them has to be true. Between the two of them, they add up to 100% of possible cases that could occur. And another way that we can use this is to basically solve this, rearrange it, and solve to see that if I tell you what the probability of event A is, I can figure out the probability of event A complement. So I can solve for this piece of the equation by simply subtracting this part from both sides. So I'd subtract it off of this side, it'd cancel out, and I'd be left on the other side with 1 minus P of A. So as long as you know the probability of event A, you can use that to find the probability of A complement, or vice versa. If I know the probability of A complement, I can use that to find the probability of event A. There are a couple of things that we kind of have to be a little bit careful with, and I just want to kind of point this out. So let's do this example. This will highlight the idea. What if I tell you that in the real world, there are, let's say this, let's say 10% of people are left-handed. So I'm going to say that event A is the event that a randomly selected person is left-handed. And I made this number up. It's probably close to 10%, but I don't know the exact number. Let's figure out what A complement is and the probability of A complement. So what is the phrasing that we would use for A complement? A complement would be that a randomly selected person is what? And the correct answer is not left-handed. Some people probably were inclined to say, instead of not left-handed, would say right-handed. So a randomly selected person is right-handed, and that would be the complement of left-handed. But it turns out that that is not quite the case. So just as a side note, A complement can't be right-handed. Right? We can't pick right-handed instead of left-handed for A complement because it excludes some cases, even if those cases aren't common. It excludes people that consider themselves ambidextrous, that can use both hands equally well, and so you wouldn't say they're left-handed, you wouldn't say they're right-handed, you would say they're ambidextrous. It would also exclude people that happen to be either amputees or people that were born without one hand or the other, or things of that nature, in which handedness doesn't really make sense. It's not something that that pertains to those individuals. So really the complement of a randomly selected person being left-handed is them being right-handed or ambidextrous or not having hands, or there's maybe other cases that I can't think of. And so instead of trying to come up with every possible counterpoint to being left-handed, most of which are right-handed, but there are a few of these other cases, it's easier to, in this case, just say not left-handed. So keep that in mind. We have to pick, the complements have to cover 100% of possible cases. Right? I can't have left-handed and right-handed because that excludes a small percentage of people that don't fit either of those two categories. And we need it to add up to 100% of all possible cases. So in this case, we are keeping it as left-handed versus not left-handed. Not left-handed is sort of a blanket statement that covers people who are right-handed, ambidextrous, missing hands, whatever the case may be. So keep that in mind. But using that, we can ask the question now, what is the probability that someone is not left-handed. Right? So basically what I'm saying is we just said that the probability of event A, which is being left-handed, that it is 0.1. 10% written as a decimal is 0.1. And according to our formula up here, the probability of A plus the probability of A complement has to add up to 1. So if I add the probability of A complement, which is something that we don't know, it has to add up to 1. So what number has to go here for these things to add up to 1? Well, we could solve for it by subtracting 0.1 from both sides, but you can probably just do this one in your head. This implies that the probability of A complement is going to be 0.9. So 90% chance that somebody is not left-handed. This is how we can use the rule of complements, and it's also going to be a really useful tool going forward. We're not just learning this once and forgetting it. We're going to use the rule of complements a fair amount going forward in some of the later sections of the semester that we're going to look at. So keep this in mind. Here's our two main rules. We have the rule of complements. We have the general addition rule back up here. Both of these are going to be useful ideas, and they will show up again later on in the semester.